Alright, digital polysomnography part 5B. Remember, you don't have to totally understand all this stuff. Totally. If you understand the general concepts of it, that is what we are looking for. Signal measurement. To measure an incoming signal off a patient, we have a couple variables. The first is time, and it's represented on the horizontal axis going from left to right. That's the x-axis. It describes the period or length of a wave. The scale we use is 1 centimeter equals 1 second. So every centimeter that the paper travels is another second that goes by in a sleep study. A paper study would need at least 30 centimeters of paper to record 30 seconds on one sheet. Amplitude measures the height or voltage of a wave, and it's represented on the vertical up and down or y-axis. In polysomnography, the actual voltages are so tiny that we measure them as microvolts, meaning a millionth of a volt, and are abbreviated as the Greek letter mu and a V. The scale of 50 microvolts per millimeter means that it takes a voltage signal of at least 50 microvolts to make the pin deflect 1 millimeter. So if a pin deflected 4 millimeter, the voltage coming from the patient would be about 200 microvolts. And that is a standard for polysomnography. We refer to it occasionally as sensitivity. And we'll talk about that in a little later. Frequency and amplitude can be combined into a waveform scale legend that can be displayed over signal tracings. They are similar to like legends on maps that show you distance in miles. These are helpful when screens are resized to fit different desktop workstations and different monitor configurations, so that the technologist will always be able to relate the waveforms to a known quantity. Another useful software tool commonly in use is known as the voltage cursor. Placing the mouse arrow or cursor over a tracing will display the incremental changes in voltage and frequency along both axes. These are mostly useful when considering the amplitude of delta waves, which have the requirement of at least 75 microvolts. So increasing the sensitivity means that higher voltages are represented in the same amount of space, so increasing the sensitivity will decrease the size or amplitude of the signal on the screen. It essentially boosts the signal to make it a little bigger on the screen. However, too much or too little sensitivity can make the waveforms too big or too small. These functions we typically leave alone on the software. The AASM recommends sensitivity settings for EEG channels at 7 microvolts per centimeter. Remember, there are tons of different frequencies and signals coming off of any given body part. In order to get very specific frequencies for EEG, EMG, EKG, and EOG, we can use filters to assist in getting rid of the extra signals. A low frequency filter sets the lowest limit of frequencies allowed into the signal. If you set an EEG low frequency filter of 0.3, most of the signals below 0.3 Hz will be eliminated because 0.3 is the lowest frequency you're allowing in this filter. So when the low frequency filter, also known as the high pass filter, is set, the frequency above that number are allowed in. On the other hand, the high frequency filter assists in getting rid of higher frequencies. For EEG, we are generally looking for 35 Hz because we want to have just at least 2 times the signal frequency recording because of the Nyquist theorem, which we'll talk about in a second. When we set the high frequency filter or the low pass filter to 35 microvolts, that means everything above 35 microvolts will be excluded from the signal. Now that we have a low frequency filter of 0.3 and a high frequency filter of 35 microvolts, 35 hertz, our frequency band, or all the frequencies we potentially are looking for, are between 0.3 and 35 hertz. Sometimes you can use these filters to get rid of artifact, but I generally try not to adjust them because you're also setting that frequency to the source signal, which may eliminate some of the original signals. For sweat artifact, look about it, or think about it. It makes it look like slow waves. You can increase the low pass filter from 0.3 to 1, and that should eliminate some of the sway we see. That's another name for sway artifact. You may also hear the term salt bridge artifact, which is the same thing. The sweat is connecting the electrodes with its salinity. This is a frequency response curve. We'll have a whole part on this. By setting the low frequency filter or the high frequency filter cutoff frequencies, which are the numbers you're setting, we choose the window or the frequency band that we are interested in viewing. This is a filter response curve. It describes the frequencies that the majority of the recording will show. These filters do not cut off all frequencies. It's a gradual cutoff that reduces logarithmically. So you can see here's 0.3 low frequency filter. And so everything below that would be filtered out. And then you've got, here's 35. So everything above that would be filtered out. So you have this kind of window-ish looking bell curve, and that's all the frequencies that you're going to get. You do not see these in sleep studies. Okay? So understand that this is just a graph that is demonstrating or explaining how low and high frequency filters cut off certain frequencies. That's all. A machine calibration is performed so that there is recorded documentation of the validity of the filter settings. The machine calibration shows the effect that filters have on a supplied square wave signal. A square wave signal is a signal that oscillates or goes back and forth between positive and negative constant calibrated voltage. This was one of the concepts that I had some difficulty understanding when I was going through sleep school. The important thing to remember is that this calibration involves the machine sending on and off signals to see how the filters react to them. And it should look something like this. How quickly the signal falls back to the baseline is determined by a filter's time constant. When a DC voltage is input, the signal at the filter output is changing almost immediately. After the signal reaches the peak, it immediately starts to decay back to the baseline, but slower. The fall time constant is the time it takes for a signal to decay 37% of its original voltage. The rise time constant is the time it takes for the signal to reach 63% of its peak voltage. Notice that higher filter cutoff frequencies settings result in a lower fall time constant and vice versa. This is important because it allows us to illustrate to all who would inspect our recorded data that we were collecting data with known, verified, correct filter settings, and all of our stuff would be legitimate. The rise time and fall time for time constants may be on the exam. But the important thing to remember are the percentages, 37% and 63%. And these are time constants. We will talk more about these later also. This is a pretty good representation of what machine calibrations look like. If your machine ever starts doing something else, make sure everything's plugged in, make sure your filters are set correctly, and then ask your supervisor because you might have a bad amplifier. The purpose of the 60 Hz and 50 Hz in some countries filter is to eliminate noise caused from power line interference from the record. The record should be as free from 60 Hz noise as possible without using a filter because strong 60 Hz interference may result in amplifier saturation. So check out these signal tracings here. This is a 60 Hz artifact. It's just a big black line. That's an electrical interference. And here it is also. Looks like some right there too. Analog to digital conversion translates continuous bioelectric or analog and ancillary device signals into discrete numerical values, usable numerical values. The analog to digital converter is capturing analog signals periodically at a sampling frequency or sampling rate, and it's creating numeric data points or samples. This next statement is true for all recording, whether electrical recording or even musical recording. In order to properly reproduce the analog signal waveform, this sampling frequency needs to be at least 2 times higher than the highest frequency that is being measured. This is known as the Nyquist theorem. If the criteria is not followed, then the incoming signal that are above f over 2 will be aliased or replaced with frequencies that are different from the original signal when the waveform is reconstructed or viewing. Aliasing means the frequencies are recurring at a rate that's not displayed reliably. So there is a signal artifact because the amplifier is desperately trying to accurately show the signal. Think of it like this. You know when you get a low quality video on YouTube and it's pixelated, meaning the image is blocky? It can sometimes make the video or picture look really different because there isn't enough resolution. That's the same thing with aliasing. Because there isn't enough data sampled, it will look different. So, because the highest frequency of brainwaves we typically look for are between 14 and 16 beta waves, we double that, and then add a little bit more for a high frequency filter of 35 hertz. You may not be old enough to remember when MP3s became a thing, but it was great because you could hold a whole song on a computer in just a few megabytes, which could take forever to download. But if you listen to a high-quality CD recording against an MP3, you would notice the top high-end sounds are gone, like the cymbals. They sound real staticky and not very clear. So that's aliasing, making the cymbals sound like not cymbals, but they're trying to give you a signal that sounds like it, but it just doesn't happen. The sampling rate of a modern analog to digital converter can actually exceed 32,000 samples, and by using the Nyquist sampling theory, this results in a reliable frequency spectrum of up to 16,000 hertz. The raw data stream can be filtered in software before secondary sampling, which we call decimation, which creates an output data stream typically at a sampling frequency of around 256 to 512 hertz. This technique is called oversampling and allows a high degree of flexibility in selecting output data rate and eliminates aliasing without the use of large and expensive electronic components for low frequency filtering. Multiplexing is the combination of multiple signals in one stream in order to allow data conversion to be performed by fewer ADC components, analog to digital conversion. Alternatively, multiple independent analog to digital converters may be employed, a dedicated ADC for each channel. With proper design and modern components, adequate signal quality can be achieved with either approach. In order to accurately display the EEG signal waveform, a minimum of 12 bits or 4096 voltage points with a sampling rate of 500 Hz is required. In practice, most systems use at least 16 bits or higher analog to digital converters, allowing larger dynamic range and smoother signals. The number of data points may be further reduced by amplifier or application control software depending on relevant physiological characteristics related to the actual rate of signal change. And this allows for storage constraints to be met. The final result is accurate and a noise-free representation of the original signal at the desired electrode pairings, sensitivity, and filter settings. Calibration is the determination and documentation of the accuracy of a measurement or an observation. Biocalibrations should not be confused with system or instrument calibrations. Biocalibrations are just for the patient to demonstrate that the instruments are picking up the correct signals. Instrument calibrations ensure the measurements that are turned into signals are accurate in their length and amplitude. To document the scale used when viewing the recording, perform and record a time constant and square wave calibration. Usually that's just called calibrations. Many systems will produce a channel by channel scroll of a square wave which will trace a DC 50 microvolt per centimeter on and off signal, meaning every second when the DC is on, the signal jumps and stays at 50 microvolts. When the DC signal is off, the tracing falls down to the electrical baseline or zero. An impedance check is not really a calibration, but it does verify that the electrodes have a good connection. When on, the impedance check produces an electrical stamp on the record, the actual sleep study, and shows the contact impedance values of the applied electrodes, and it documents the actual values in kiloohms. Again, we want to aim for a target of less than or equal to 5 kiloohms, with the electrodes being relatively even. Although all electrodes need good impedance values, have to be low and secure. Although all electrodes need a good impedance value, the common ground and reference electrode impedance have to be low and secure because they are tied to each of the other signals. Most PSG systems have integrated or built-in pulse oximetry that conforms to AASM standards for accuracy and sampling rates. Integrated pulse oximeters are designed to do zero calibration automatically. When using an external pulse oximeter or a totally different machine from the polysomnography to read the oxygen, we compare the readout with what is being displayed on the PSG monitor. When ancillary, or a part of the PSG equipment, CO2 monitoring devices, we use a DC input box on the amplifier to connect it to the PSG. Calibration involves assigning a voltage range to the maximum and minimum measurement values. Follow the manufacturer instructions to output 0 volts from the device and assign the 0 value on the PSG system. You are connecting the dots between what is this device saying is 0 versus what your computer is saying is 0. You're synchronizing your watches, so to speak. Then you're going to output 1 volt from the device and assign the 100 value, and then you save the calibration. That's not totally standard for all PSG systems, but it is very similar. That seems just like Compumedics, how you would do it on their system. You will have the O2 or CO2 device send a signal that represents either the low or the high end of the values you want, either 0% or 100% for oxygen, and typically between 0 and 212 for most CO2 machines. Once you send those signals, you save them on your sleep program as the highest and lowest values. When the patient has the pulse ox on, the pulse ox unit reads the oxygen level as an analog signal and translates that into a voltage like 0.973 volts, which would maybe translate into the PSG system as 98%. The same occurs for CO2. A lot of the times these capnographs move from room to room when they're needed, and they have to be calibrated before you use them each time. In the end, follow your P&P manual. It will have a detailed explanation of how the provider wants the calibrations to be documented and performed. Every lab is different. When I worked in Raleigh, to calibrate the pulse ox, there was a function on the pulse ox machine that would say send 1 volts, which would artificially represent 0% on the pulse ox, and then send 0 volts, which would artificially represent 100% on the pulse ox. For capnographs, we would, if we hooked the cannula up just to the machine and not on anybody, the value would be 0.0 mercury, or millimeters of mercury, which is the lowest figure we would want for CO2. If we unplugged the cannula, the signal sent would actually be a signal of 212, which is the highest signal we would want. and I would save each value for high and low in the PSG system. Uh, this might sound super complicated, but once you get in the lab and you do it a few times, it'll click and you'll understand why. Most CPAP manufacturers have developed flow generators capable of multiple measurements, including pressure, flow, and leak rate. Calibration of CPAP to the PSG system involves assigning a voltage range to the desired minimum and maximum values according to the table you see here. These numbers represent what the voltage gets translated into the PSG as if the PAP was sending 1 volt. That represents 30 centimeters of pressure on the PSG. So that means that the machine was sending 0.5 volts, it would represent 15 centimeters of pressure. The performance of calibrating equipment is most critical when it involves assigning quantitative rather than qualitative values to a measured signal, so numbers. A standard montage should meet the minimum criteria channel recording as outlined in the AASM manual version 2.5. The digital PSG allows the technologist to either re-reference electrodes to maintain signal clarity or to even link the two references together and provide a mathematical average of the left and right references. We do this to get rid of EKG artifact because the heartbeat is so prevalent on both sides of the body, the common mode rejection ratio takes the signal and removes it. This used to be called linked ears because you could put something called jumper cables on the mastoid references, and that would link them together to attenuate the EKG artifact. Many recording variables in different montages can be used in order to satisfy the requirements of ordering physician and aid in diagnosis. So here's the ASM guide to technical specifications as they relate to PSG equipment. This is really the important information you need to know for the exam as far as technical information has, and you should have a general knowledge of it. The more you understand what a low frequency filter does and what a high frequency filter does and what a sampling rate does, then you automatically understand what you're trying to get, and you don't really have to remember them. When I was studying this stuff, I didn't really understand filters very well, so I would order the low frequency filters and remember the order of the equipment channels and actually memorize it in that order. But now, because I'm so familiar with this kind of stuff, I don't really have to remember it. I just know and remember what it means and how it works because I know what it does. Digital video cameras are synchronized to the PSG recording and bring a valuable diagnostic tool to the digital PSG. The analog signal from a high-resolution camera is converted to a digital format video and time synchronized with the raw PSG data stream. This allows for quick navigation to desired epochs to view video synchronized with the recording. Directional or omnidirectional microphone or speaker configurations make it possible to communicate with the patient and to capture even the faintest sounds in the recording bedroom. Not only do we record PSG data, we have to keep accurate records and archives of the raw data. Typically, there is a database of the patient's demographic and clinical values. A lot of the times it's the EMR. There are also a log of the studies that are run. Sometimes all this can be imported into the PSG system, allowing for seamless transition from provider to provider. There are many ways to store data. It's a good idea after a while to take the data from the hard drives and put them on physical media like magnetic tape, external drives, DVDs, or something like that. Nowadays, with cloud applications, we can back up and archive studies all online without physical media needed. However, if the cloud is down, you have no access to any of your data. Data has to be saved for years in some cases. Depending on the patient volume in your lab, you may have a third-party storage company that deals with your overflow. There are some allowances that the ASM gives. For example, after the study has been interpreted by the physician, the video can be cut to save data. If you do this, it's a good idea to capture and keep at least a few epochs of the patient in REM supine if possible. If the study is a parasomnia montage or a seizure montage or something interesting happens during the study, the video should be kept as is. This is important in view of the fact that sleep medicine is now particularly concerned with differential diagnoses and comorbid conditions. PSG systems will export study files in EDF, which is similar to PDF, and other file formats so that patient records can be viewed across all sorts of platforms. Modern PSG systems will also integrate with spreadsheets and word processing programs so that you can just generate a report, and it can be tailored to show data in every way imaginable. Digital PSG has become a more reliable with the inclusion of such technology as automatic disaster recovery, which in the case of power outages automatically restarts the system and appends to the existing record, and that's fantastic. Compumedics and Cadwell both do that, and it was great. Digital polysomnography has also made portable monitoring possible, also known as out-of-center testing. Most manufacturers now offer portable amplifiers that do not sacrifice any channels typically included in normal facility-based polysomnography. These devices can be set up in a facility and go home with a patient. The technology on the schematic basis is quite similar to the full PSG with the option of video and video capture. This technology is categorized as a Type 2 device. Type 3 and 4 portable devices are simpler devices that really just do the pulse ox, effort, and nasal pressure. So, throughout this electricity course, we're going to bring back a lot of these things like time constant and filters and things like that, and Ohm's law. So, something I did when I didn't understand it, I faked it till I made it. And it won't be long until you make it. That's the nice thing about that. So, if you really want to understand these things, keep going because we're going to get further into it. Also, I'm going to keep repeating these concepts, and I'm going to try and use different words each time because sometimes just the way you change up the way you say something can make all the difference if towards someone understanding and someone not. Also, if you YouTube some of these things and also include the word simple or something, simple electric circuits, there are millions of videos online about electricity, and that's a great resource that I have used as well. All right, see you in the next one.